Hello, welcome to Engineer's Mindset. So let's say we have this beam and we have to determine the reactions at the supports A and D. Now in this case, this beam is carrying a uniformly distributed load between point A and point B. Alright, so we start with outlining the free body diagram. So we'll bring back the beam. So I said in the previous video that for a pin support, this is a pin support, and for a pin support, we have two reactions, one vertical, so we simply have RAY, and one horizontal, so we simply have RAS at point A. Also, between point A and B, we have a uniformly distributed load. Now, to convert a UGL to a point load, of course, for us to be able to determine these reactions, we have to convert the UDL to a point load. And to convert the UDL to a point load, simply multiply the intensity of the UDL to the length covered by the UDL. So the length of the UDL there is 2 meters. Therefore, to convert this to a point load, simply 8 times 2, and it becomes 16. So the UDL is between point A and point B. Now, this point load, 16 kilonewtons, you place it at here, the middle of the length covered by the UGL length. Okay, the UGL length is 2 meters. Middle of 2 meters is simply 2 divided by 2, and that is 1. So from each end, the UGL is 1 meter apart. So you have this. Okay, the value is the value is 16 kilonewtons. So from point A, the point of the load is 1 meters. From point of the load to point B is also 1 meters. Alright, so to convert the UDL to a point, you simply multiply the UDL load to the length. So it becomes 8 times 2, that's 16 kilonewtons. Then place it at the middle of the length. So 2 divided by 2, 1 meter. So that's the middle. From A to the point of the load is 1 meters. From B to that same point of the load is also 1 meter apart. Alright, so at point C you have a 10 kilonewtons load. This is 10 kilonewtons. Point C. Meanwhile, at point D we have a roller. And the roller will just have one reaction, normal to the surface. So this is R, G, Y at point D. Okay, this distance is 3 meters, Y is 2.5 meters. Okay, so that's what the free body diagram looks like. After obtaining the free body diagram, the next thing to do is to employ the equilibrium equation. So from static equilibrium law, we have that summation f of x is equal to 0. Also, summation f of y is also 0. So we'll start with the first one. Summation f of x equals 0. So every force pointing to the x-axis on this beam equated to 0. That's what the law is saying. Sum all the forces in the x direction, that's all the horizontal force, and equated to 0. And if you take a look at this beam, only one force points to the x direction. Only one force points to the x direction, and that force is simply RAS. So that simply implies that RAS is equal to 0. So you have this. The next law is summation f of y is equal to 0. Now, when employing the vertical law, consider always vertically upward force as positive, and then vertically downward forces as negative, always. Okay, so if that's the case, we have RAY pointing upwards, so it's positive. So we simply have RAY. Okay. Now we have 16 kilonewtons force acting downwards, so it's negative. Okay, so minus 16. We also have 10 kilonewtons force acting downwards, so it's negative. Minus 10. And then finally we have RGY acting upwards, so it's positive. So we have plus RDY, and this is equal to 0. Okay, so RAY minus 16 minus 10 is actually minus 26 plus RDY, and that's equal to 0. So let's send minus 26 over to this side of the equation. We simply have that RAY plus RDY dy is now equal to, this becomes 26. Call this equation 1. So notice now that equation 1 is what? An equation that involves two unknowns in one equation. So it's very, very much impossible for us to solve. So in the previous video, I explained that once you get to this point, the next thing to do was simply what? Take moment of force about the point on the beam where you have numerous of forces. So on the beam, we have two forces at point A, and then we have single forces at each of these points. So the best possible place to take our moment is simply what? At point A, so that the effect of these two forces will become what? Nullified. So take moment at point A. Take moment at A. Okay. Summation of moment at point A is equal to 0. Let's choose clockwise moment to be positive, anti-clockwise moment to be negative. Okay, so forces that take moment in the clockwise direction should be positive, while anti-clockwise moment should be what? Negative. So since we are taking moment at point A, it means that the moment of these forces RAY and RAS about point A automatically becomes 0, nullified, because moment is force times distance. So if you're taking moment at point A, there is no distance between point A and these two forces. They are all at point A. So it becomes force times 0, since there is no distance between them. Force times 0 is automatically what? 0. So those moments, their effect is completely what? Out. So we now focus on the remaining forces on the beam. Starting with what? The 16 kN force. 16 kN force is acting downwards. So the moment of this force about point A, it will turn all the way from this direction to what? To get to point A, which is what? Our direction of moment, positive, clockwise, which is our direction of moment. Clockwise means it's positive. So it goes clockwise to get to what? To point A, so it's positive. And distance it takes to get to point A simply was 1 meters. So the moment of this force is simply what? 16 times distance it takes to get to point A, which is 16 times 1. So you simply have 16 times 1. Also, we have a 10 kN force that's also pointing downward. This force will go all the way from this side towards take moment about point A, which means it also goes clockwise and is positive. Our direction of moment is positive. Distance it takes this force to get to point A is simply 3 plus 1 plus 1. That's 5 meters. It takes 5 meters for this force to get to point A, and it's positive because it's clockwise. So you simply have plus 10 times 5. And then finally, we have RDY, which is reaction at point B. This force is pointing upwards, so the moment of this force will go all the way in this direction to get to point A. And this direction is what? Negative. It's anti-clockwise the direction we choose. It's negative, our direction. Okay? So it's negative direction, so it's negative. Alright, so that means you have total distance to take this force to get to point A is simply 2.5 plus 3, that's 5.5. Plus 2, that's 7.5, okay? So it takes 7.5 to get to what? Point A. So we simply have minus R dy times 7.5 is equal to 0. So you have this. Okay, so let's expand the bracket now and see. 16 times 1 simply gives us 16 plus 10 times 5 simply gives us 50, okay, minus 7.5 R dy equals 0. So 16 plus 50 is actually 66. Okay, plus 7 minus 7.5. So 66 minus 7.5 R dy equals 0. So let's send minus R dy over to this side of the equation. Negative sign crosses an equal sign becomes positive. So we simply have that 66 is actually what? 7.5 RDY. Okay? So to make RDY subject, we simply divide both sides by the coefficient of RDY, which is 7.5. So we are simply going to have like RDY is simply 66 divided by 7.5. Therefore, RDY is now equal to. So that gives us 8.8 kilonewtons. So that's the value for the reaction as support G. So simply substitute this reaction RDY into equation 1. So that will help us to find the value of RAY. So we simply substitute that into equation 1. So we simply have RAY So we simply have RAY plus, in place of RBY, we have 8.8, and that's equal to 26. So therefore, RAY is now equal to 7 plus 8.8 over to this side, it becomes minus 8.8. So we simply have 26 minus 8.8 kilonewtons. So that simply implies that RAY is simply 17.2 kilonewtons. So this is now the reaction at point A. So RAY signifies reaction at point A, or this point, while RBY signifies reaction at point B. Alright guys, in the next video, I will talk about the uniformly varying load on the beam and how you can determine reactions at those supports. Alright, thanks and cheers.